Hello learners, welcome to this course on Embedded System Design using AT89C51 Microcontroller. In this tutorial, I will be discussing about on how to configure and program external interrupts. So we have two external interrupts supported by the microcontroller. We would like to see how to configure it and how to program it. So an interrupt is a signal generated by a hardware or software when a process or an event requires an immediate attention. So an interrupt is usually given by a peripheral device. Either it can be an internal peripheral or it can be an external peripheral. So once a process is completed or once a process needs to be initiated, an interrupt signal can be generated by the peripheral device. So this interrupt signal goes to your CPU, so thereby the CPU executes the program related to the interrupt. So the internal peripherals which are supported are timers or counters or UART. External peripherals like ADC, switch, keypad or keyboard, joystick, mouse, etc. are supported. So for example, let us take a keypad. Whenever I press a switch on a keypad, it can generate an interrupt and it can be communicated to your CPU. So thereby the CPU can execute a program such a way that it will identify whether it is a valid key press or not, and then it can identify which key is pressed, and that identified key can be sent to some application programs like Word, Notepad, WordPad, etc. So whenever a peripheral wants to use a CPU, it will make a request. So upon receiving a request, the CPU will try to execute a program related to that peripheral device. So here I show a typical AT89C51 microcontroller which has internal peripherals and also external peripherals can be connected. So this internal peripherals can also generate an interrupt, same way external peripherals also can generate an interrupt. So two external peripheral pins are supported in your microcontroller, which is INT0 bar and INT1 bar. So we can connect two peripherals outside your MCU, and this peripherals can request for executing a program by the CPU. So if we see the actual process involved, so a CPU will execute a program from the memory. So it will take instruction 1, instruction 2, instruction 3, so like that it keeps on executing a normal program or a main program. So let us assume a peripheral wants to use a CPU, or the peripheral wants the CPU to execute a program related to that peripheral. In that case, interrupt is generated. So when the interrupt comes, what happens? The current instruction execution by the CPU is completed, and then the context in the sense the supporting registers for the main program and the return address for our main program all are saved onto a stack memory, and then the program execution goes to an interrupt service routine. So interrupt service routine is nothing but the program related to the interrupt. So then CPU starts executing the ISR, interrupt service routine. Upon completing your ISR, the CPU comes back to the main program. So in order to have a seamless execution of instruction, the context which is saved earlier in the stack memory is brought back to the main memory. So thereby the normal main program continues its operation. So that is how the interrupt is being serviced by the CPU. So basically, the CPU will execute a program from a memory, so it will try to carry on its routine work. If an interrupt comes, what happens? It tries to respond to that interrupt by executing a program related to the interrupt. So upon completion of the interrupt, it again comes back to its main program. So as I said, our microcontroller, it supports interrupts both from internal peripheral as well as external peripherals. In case of 89C51 microcontroller, it supports 5 interrupts. So out of 5, 3 are internal peripherals and 2 are external peripherals. So the external peripherals are INT0 bar and INT1 bar. Internal interrupts are timer 0 interrupt, timer 1 interrupt and serial communication interrupt, both the transmission interrupt and reception interrupts. So since it supports 5 different interrupts, the interrupts can come at any time. So if 2 or more interrupts comes simultaneously, then how the CPU needs to process, or the CPU needs to execute the program related to which interrupt, that needs to be determined. So in order to do that, we have an interrupt controller. So the interrupt controller, it accepts all the interrupts and priority is set for each and every interrupt. Depending upon the priority, the interrupt controller gives an intimation to the CPU that to execute a particular ISR depending upon the priority of the interrupt. So the interrupt controller makes a decision to give an indication to the CPU that which interrupt should be serviced. So in our AT89C51, this is a architecture of your interrupt. So here, as I said, we have 2 external interrupt pins. One is INT0, another one is INT1. So these 2 pins, INT0 and INT1, can be connected with any external peripheral devices. So once an interrupt is generated, so this interrupt can be recognized upon 2 levels, either on a falling edge or it can be on a low level interrupt. So in order to select what type of interrupt identification mechanism will be used, we will be using this bit called as IT0 and IT1. IT0 is for INT0, IT1 is for INT1. So if this IT0 is 0, then our CPU will recognize for low level interrupt. If IT0 is 1, then it will recognize for falling edge interrupt. Falling edge in the sense high to low transition. So this IT0 and IT1 bits are available in your TCON register, timer control register. So once an interrupt is generated, automatically it will set the flags. So for INT0, we have a flag called as IE0. For INT1, we have a flag called as IE1. So once an interrupt is being given to the pins, then it automatically sets the flag. So as soon as the CPU responds by going into an ISR for executing it, these flags will get cleared. So when interrupt occurs, the flags will be set. As soon as the CPU goes to the ISR, these flags will be reset. Then in order for this interrupts to get communicated to your CPU, we have 2 switches. One is EX0 and EA. So EX0 is an enable for your INT0. EX1 is an enable for your INT1. So this is something like a individual switches. If this INT0 needs to be communicated to a CPU, then enable interrupt 0 should be active, and also enable all the interrupts should be active. So this is a common switch for all the interrupts. So if I switch off this enable interrupt, then no interrupts will be communicated to your CPU. So in order for INT0 to be communicated, then we should have EX0 to be 1 and EA0 to be 1. So then only this INT0 interrupt will go and reach your CPU. Same way, if INT1 needs to get communicated to your CPU, then we need to enable this EX1 and EA1. So then only the interrupt will go and reach the CPU, then CPU can execute a program related to that interrupt. So this EX0, EA, EX1, EA are available in your interrupt enable registers. So we are going to use 2 important registers. One is TCON register. In TCON registers, we have IT0, which is used for selecting the type of interrupt, whether it is a falling edge interrupt or low level interrupt. Same way, IE0 is a flag register for an interrupt. So these 2 are available in your TCON register, whereas IE0 and EA are available in your interrupt enable IE register. So now let us look at those registers. So TCON, as I said, is right. So I have IT0. So IT0 indicates 0 to this bit will be selecting a low level interrupt. 1 to this bit will be selecting falling edge interrupt. So this IE0 and IE1 are your flags for your external interrupt 0 and external interrupt 1. IT1 is a type of interrupt selection for your INT1. Next is your IE register. So IE register is interrupt enabled register. So here you can see bit 0 is EX0, which is a control switch for enabling your INT0. Same way EX1 is a control line for your enabling your INT1. And EA is used for your enabling all the interrupts. Next one is your priority register. If multiple interrupts comes simultaneously, then how it can be recognized. So here it shows the order PX0, PT0, PX1, PT1, PS. If timer 2 is there, then PT2 bits. So the order of priority is from PX0 as higher priority, PT0 is next highest, PX1 is third, PT1 is fourth, and PS is fifth. So PX0 is priority for external interrupt 0, PT0 is priority for timer 0, PX1 is priority for external interrupt 1, PT1 is a priority for your timer 1, PS is a priority for your serial port interrupt. So if timer 2 is available, then PT2 will also play a role. And each interrupt priority can be in two levels, either in level 0 or level 1. So level 0 means it is going to be low level interrupt, level 1 means it is going to be a high level interrupt. So if I put PX0 to be 0, PX0 to be 0, then external interrupt 0 is configured as low level interrupt. If PX0 is set to 1, then external interrupt 0 is configured as high level interrupt. So each interrupt can be in any of the two levels. It can be either in level 0 or level 1. So level 0 means it is low level interrupt, level 1 means it is high level interrupt. So same way all the other interrupts can also be in either low level interrupt or it can be a high level interrupt. So logic 0 to the bit will make it low level interrupt, logic 1 to the bit will make it high level interrupt. So in this tutorial I am going to talk about how to configure and program this external interrupt. So here we will be using integrated development environment, which is Micro C Pro for AT51. So where we will be writing our embedded C program, convert that embedded C program into your hexadecimal file. Then we will be building our circuit in Proteus 8 Professional. So the important thing is we need to configure our external triggering either to low level or falling. And another important aspect is here in your ISR, in your interrupt service routine, the variables whichever we use should be declared as a volatile. And if I use a serial data while executing a ISR function, it will be lost. So if you receive some data through serial port communication, UART communication, whenever we are executing ISR, that will not be considered or that will be lost. So here what we do, we take AT89C51 microcontroller. So I am going to connect a switch to port 3.2, which is your INT0 bar pin. So whenever I press the switch, a falling edge or low level will be configured, and depending upon that interrupt, we are going to do some change in the logic of your LED connected to port 2 from port 2.0 to 2.7. So this is a typical circuit which we try to build on a Proteus environment. In case of a programming, we have two routines. One is your main program and another one is your ISR. So ISR is given on the left side. So first let us talk about the main program. So main program starts with void main. So since we have connected LED to port 2, I have configured port 2 as an output port by putting 0x00. Then since we have connected a switch to INT0 pin or port 3.2 pin, we have set it as an input pin. Then IT0, I have set it to 1, which is available in your TCON register. So if I put 1, then we are configuring the interrupt for falling edge. Then EX0, in interrupt enabled register, I am setting it to 1 so that INT0 gets enabled and we enable all the interrupts. Again, all the interrupts are enabled in your interrupt enabled register. So this is the configuration part. Then in a while loop, port 2 is set with 0xFF, which means all the LEDs will be in off state. So this value will be retained for 1 second. Then port 2 equal to 0x00, then all the LEDs are in on state. Then again it will be retained in 1 second. Since it is in a while loop, it will continuously toggle the LEDs off for 1 second and then on for 1 second. So this will continue. So whenever an interrupt happens, whenever we press a switch or connected to this port 3.2, it goes to your ISR. So the ISR is shown here. So in ISR, we use an interrupt name. So I have given a name as external underscore INT0 and we specify the interrupt vector. So interrupt vector address should be specified. So each interrupt has a vector address. So the table is shown below. So INT0 vector address is 0003. INT1 vector address is 000B. Timer 0 is 0013. T1 is 001B. TARRI is 0023. So this interrupt vector means, so whenever an interrupt occurs, so our program counter will be loaded with this vector address. So in this vector address, there will be a call instruction which points to the ISR in the program memory. So wherever the ISR is saved in the program memory, so that starting location will be pointed through this address location. So when an interrupt comes, the program counter will be loaded with this vector address. In this vector address, we will have a call instruction pointing to the ISR starting point. So we set the interrupt vector address to be address EX0. So which is nothing but this 0003. Then we specify the interrupt level. So the interrupt level can be either 0 or 1. 0 means it is a low level interrupt. 1 means it is going to be high level interrupt. So here I have set it as a low level interrupt. Then ICS is an interrupt context switching. So context switching means whenever there is an interrupt, so our CPU should go from your main program to a ISR. So before moving from main program to ISR, we need to save the context. All the registers which we are using in the main program should be saved. So that after completing the ISR, when I come back to the main program, I can get back those data and I can work seamlessly. So whether I need to have a context switching or not. So that can be specified by this ICS, interrupt context switching. So we are setting it to auto mode, so automatically context will be saved. So whenever an interrupt occurs, it goes here. Inside the ISR, what is the first step which we are doing? We are disabling all the interrupts. Because if I get another interrupt, when I try to execute an ISR, if I get another interrupt, then there is a chance that I can, if it is a higher priority interrupt, then we need to nest to the another ISR. So in order to avoid that, what we do, we disable all the interrupts. Then I am going to change the logic of your LEDs in port 2 by putting 0xAA. First, initially in main program it is all the LEDs are off, all the LEDs are on. In ISR we put it to be AA and 55. So AA means 1010 1010. So wherever I have a logic 0, that corresponding LED will be on. Logic 1 connected to an LED will be in off state. So 550101 0101. So again, wherever we have logic 0, LEDs will be in on state, otherwise it will be in off state. So when I want to come out of the ISR, we enable all the interrupts so that next time when an interrupt occurs, it can be recognized. So it comes back to the main program. Again, main program, all the LEDs are off, all the LEDs are on, is continuously going on. Again, when an interrupt comes, it goes to the ISR and executes this program. It comes out to the main program. So this is how the embedded C programming for your external interrupt is done. Now let us look at the Proteus environment, and then we will look at the micro C program. So here I show a typical circuit built on a Proteus 8 simulator. So where we use AT89C51 microcontroller, and we are going to connect a crystal frequency of 10 MHz to XTAL1 and XTAL2 pin, and we are going to connect a reset circuit to the reset pin. So by default this reset pin will be at logic low. Whenever I close the switch, the reset can be enabled. And we have connected a switch to your port 3.2 INT0 bar pin. So by default this pin will be at logic high. Whenever I close the switch, this pin will go to logic 0. So thereby a falling edge will be created. 1 to 0 transition will be created. So then it can enable the external interrupt, and we connect the bar graph LED to your port 2.0 to 2.7. So here the cathodes are connected to your port line, anodes are connected to a supply. So a logic 0 to the port pin will make an LED to glow. Logic 1 to a port pin will not enable the LED to glow. So this is an embedded C program created in your Micro C Pro for AT51. So here we have an ISR. So void external interrupt 0. Then we specify the interrupt vector address, interrupt level, and whether we need to have a context switching or not. So this is an ISR. This is a main program. So here in this software we also have a interrupt assistant is available. So that interrupt assistant can be used. For example, here you can see this is an interrupt assistant. So here I can give a name to an interrupt. So ext int1. Then we can specify the vector address. So since I have given int1, I can use the vector address for ex1. Then I can set whether to interrupt level 0 or 1. So in some microcontrollers, higher end microcontrollers, interrupt level 2 and interrupt level 3 are also available. So in this AT89C51, we have only two levels, either it will be 0 or 1. So 0 means low level, 1 means high level. For advanced microcontrollers, 0 means low level, 3 will be the highest level. So we can either set it to level 0 or level 1. Then we have context switching. So in context switching, again I have whether automatically the context should be saved or we need not save the context by switching it off. So this is the format for building your interrupts. So once the program is completed, we can build the program so that the C program can be converted into an hexadecimal file. So we can go to this build option, press this build button, so that the compilation will happen. So and then it will get converted into your hexadecimal file.